Okay, in this lecture, we will talk about something else, which is transformation of the differential equation by changing the independent variable. But first, let us recall the exact differential equation and how we can make it exact. So sometimes the differential equation that the equation gave us will not always be exact at first. And let's take an example here, which is root of x d squared y dx squared plus 2x dy dx plus 3y is equal to 0. So let's see here, we have, here is p0, and here is p1, and here is p2. So the condition for exactness is p2 minus p1 first derivative plus p0 second derivative, which has to be 0. But if we looked here and put the values, so p2 is 3 minus p1, if we take the first derivative it would be 2, and then p0, if we take 2 times differentiation, this would be okay, root of x. So the first derivative would be, so it would be like 1 by 2 root x. So if we differentiate this again, it would be minus 1 by 4. Okay, this would become minus 1 by 4 x power 3 by 2, I think. Right. So this would not be 0. This will not be 0. Because 3 minus 2 minus 1 by 4 x power 3 by 2, this is never going to be 0. So the condition for exactness is not satisfied now. From this equation, the one in blue, if we checked for the exactness, then it's not exact anymore. But these type of things, there are some differential equations which we can make it exact. So when making it exact, we have to multiply these things, the whole differential equation, by something. So that thing is called an integrating factor. So the whole thing is in the form of functions of x. So if we multiply it by x power m, say, okay, let's say if we multiply the whole thing by x power m, then we will get root of x power m d squared y dx squared plus 2x x power m dy dx plus 3x power m y equals 0, right? Equals 0. So then if we simplify this, then it would be x m plus half d squared y dx squared plus 2x m plus 1 dy dx plus 3x power m y, all these things is 0. So we now get this as p0 and this as p1 and 3x power m as p2. So the condition for exactness is p2 minus p1 first derivative plus p0 second derivative has to be equal to 0. So if we want this equation to be exact, then we have to put p2 minus p1 first derivative plus p0 second derivative is 0. So we will put the values here. So p2 is 3x power m. So p true is 3x power m minus p1. If we take the first derivative, we get 2m plus 1 x power m plus p naught. If we differentiate it 2 times, then we would get m plus half and m minus half. M minus half into x power m minus 3 by 2 is 0. Is 0. So if we simplify this, then we can get at the end 1 minus 2m into x power m minus 1 by 4, 2m plus 1, 1 minus 2m, x power m minus 3 by 2, the whole thing equals 0. So if we multiply two things, then we get 0. That means at least one of them has to be 0. So if we take that, then 1 plus 2m, 1 minus 2m is 0, which implies m has to be 1 by 2. So if we take m is half, then our integrating factor, the thing that we multiplied by, becomes x power 1 by 2, which is the same as root of x. So if we multiply the given problem by root of x, then we can get the exactness. The condition for exactness is satisfied. So we can make some given problems exact by multiplying it by an integrating factor. So that is how we make it exact. So an equation comes, then we can multiply it by x to the power m, then take the condition for exactness, and then find out the value of m here. Then we will get that exact condition. So if the equation involves trigonometric functions like sine, cosine, those things, then we can do hit and trial and error method. We try, then if it's not working, then we try another thing. So it's not hard in trigonometric functions also. And after we're done finding out the integrating factor, then we know that our equation is now exact. Then we can solve it just like the previous lecture. Just like how we solve the exact differential equation, we can apply that same method again. But before that, we have to check if it is exact or not. So if it is not exact, then we can find an integrating factor like this, and then we can solve it. So that would be all. Now we will look at how we can solve a differential equation by another method, which is called transformation of the equation by changing the independent variable So in our equation, let's see here, our second order linear differential equation standard form is d squared y dx squared plus p dy dx plus qy equals r. This is our standard form. So here, if we look at this equation, the independent variable is x. So everything we differentiate it with respect to x. So the independent variable is x and the dependent variable is y. So we can say that x is independent and y is dependent on x. So our method is to transform this independent variable. To transform the equation, then we can change this independent variable x to some other variables. So let's say if we put z is a function of x, so we will change this x to z. How can we do that is, if we have z as a function of x, then we can say that dy dx can be written as dy dz dz dx. So this is just the same, right? For simplicity, we can take out this dz dz and we can get the same thing. So if z is a function of x, then we can write like this. So after finding all these things out and finding out d squared y dx squared with respect to this x and z, so we can find out that we have another transform equation which can be written as d squared y dz squared now, because we are changing the independent variable x to z. So instead of x, we can write z plus p1. Here we write p1 instead of p because in the process of changing x to z, then that p may not remains the same. So we write p1 instead, then the same thing, dy dz plus now also q1 y, which is equal to r1. So our p, q, r may change during the process. So that's why we write p1, q1, r1. And if you solve this, then p1, you can take p1 as d squared z dx squared plus p dz dx all divided by dz dx whole squared. So this is our value for p1. And q1 would become q by dz dx whole squared, and r1 also r divided by dz dx whole squared. So we have to know what is r, what is p, q, and r, and then remember these formulas, how to find out p1, q1, and r1. Now, what we need to have to find out the value of p1, q1, and r1 is that we need to have the value of z, right? So we need to have the value of z. So we have to choose z such that this p1 becomes 0. So the coefficient of the first derivative becomes 0. So if we get this 0, so the value of p1 is d squared z dx squared plus p dz dx whole divided by dz dx whole squared, which is equal to 0. So the denominator, we cancel it out. So if this is the case, then dividing by dz dx, then we will get log dz dx equal to minus p, which is the integration of p dx. So if this is the case, then we can find out z such that z is equal to integral of exponential of minus of integral of p dx and the whole dx. So if we find out this integration, then we have the value of z. So if this is the case, then the equation reduces, because p1 is now 0, so it reduces to d squared y dz squared plus that p1 thing is 0, so plus q1y equals r1. So here we take q1 is equal to q by dz dx whole squared, right? So when finding out, when solving the problems, we will always take this q1 to be constant. So this is constant. So we'll solve one example to make it clear. So our example would be d square y dx squared plus 2 divided by x dy dx plus a squared by x power 4y equals 0. Suppose this is our equation. So now we want to solve this given problem by changing x to z. So we have to choose z. We have to find out z. Okay, choose z such that dz dx whole squared is equal to q. So this we get it from the formula of q1 here. q1 equals q by dz dx squared, which is taken to be constant. So if this constant multiplied by, okay, if we cross multiply this, dz dx whole squared would come here in the numerator, which would be equal to q. So we can take, without loss of generality, that q1 is 1. So if q1 is 1 here, if this is 1, so we can take this one here, then we will get this thing. dz dx whole squared is equal to q. So let us look at the given problem here. Our p, right, this is p and this is q. A squared by x4 is q. So that means here this is a squared by x power 4. So after that, what we have to do is we want to find out z. So dz dx the whole squared, we have to eliminate this squared. So that means by taking roots we can get. So if we take the roots on both sides, then it becomes dz dx equals root of a squared by x power 4. So if we take the square root of this, then we get dz dx is equal to plus or minus a by x squared, right? Then we want to find out z, so we just integrate it. Just integrate integration of dz, and this dx would become here, would come here, then plus or minus. And here one thing we have to notice is that we have to take the positive part, not the negative part, so it would be easier to solve. So a by x squared dx, and we integrate this one. So integration of dz is just z, so we will get our z. So integration of a by x squared is a is constant. X1 by x squared integration is by, okay, this is x, right? So before taking this, we can still do here, this is plus or minus, so it would be plus or minus here. So we will take the value, the positive value, as the value of z. So we can take z is equal to a by x. So if we know z is equal to a by x, then we can put it here in the formula of p1, q1, and r1. Then we can differentiate that z with respect to x 2 times or 1 time. So we can get the value of p1, q1, and r1, right? But while choosing this, as taking q1 constant, we already reduced that p1 is 0. And when we find out, then r1 becomes also 0. So that means p1 is 0, r1 is 0, and our q1 becomes 1 if we find out the value. Then if we put all those things, we have d square y dz squared plus q1y equals r1, which is the reduced transformed equation. Then if we put the value of q1 here, q1 is 1 and r1 is 0. So we have d square y dz squared plus y equal to 0. So there is no right hand side, the right hand side is 0, so that means we have to find out only the complementary function for our solution. So if we find out the complementary function, just like before, then we will get our complementary function as, let's say C1 is a constant, cos of z plus C2 sine of z. So this is going to be our solution. So y equal to C1 cos z is a by x. So we will change the z to x again as the original one. So sine a by x. So this will be our complete solution here. So that is the way to solve the given problem by transformation of equation when changing the independent variable x to z.